exploration to the world of AI, ML, and DL. I once again welcome Mr. Nithin Prince John for the session. Okay, over to you, Nithin. You can now start the session.
Okay, ma'am. In this session, we are basically going to into the depth of deep neural networks. And before going to the artificial neural network, we need to have a thorough understanding on what exactly a biological neuron is. Basically, our brain consists of a large interconnected networks of biological neuron. And as shown in the slide, this is the picture of a single neuron, single biological neuron. And we can find there are some components like dendrites through which it receives signals from other neurons. This is the picture of a single neuron. Likewise, we have billions of neurons in our brain. Okay, here we have the dendrites, and through dendrites we are receiving the input to this neuron. And then we have the cell body. Cell body is this one, and in this cell body we are actually processing the information, and we have an axon through which it will output the signals to the next neuron. And there is a point known as synapse. If two neurons are connected like this, then this is the connection of these two neurons, and this is referred to as the synapse, through which it receives input to the next neuron. This is the basic diagram of a neuron. This is the cartoonistic representation of a single neuron, and we normally know that we have several organs, and through these organs we are giving the inputs to the biological neuron. Based upon a picture, we need to decide whether we need to laugh or not. And we can hear the sound through our ears, and we can see this visual through our eyes. The input from the eyes is fed to the neuron through the dendrites, and likewise the sound through these ears is fed to this neuron through the dendrites. And based upon this, it will decide whether to fire this neuron or not. Okay, and this is not the full concept. This is the cartoonistic representation of a single neuron. But in our human brain system, we have billions of neurons. Here, there are a lot of neurons that are arranged in a multi-layer fashion, and these organs are directly connected to the lower part of these neurons, and these neurons are connected to the second layer of neuron, and likewise so many neurons are there, and this is the final layer of this full neural architecture. And at this point we will decide what will be the output, and based upon these neurons, based upon this input, the neuron will decide whether to activate, whether to laugh or not. Okay, this is the complete illustration of the biological neuron. And in our brain, we have average, average human brain has around 10 raised to 11. That means 100 billion neurons are there. And each neuron will perform a specific role. For example, here we have 4 neurons, and 3 neurons are at the first layer, and we have 1 neuron at the second layer. This neuron will fire only if the visual is funny. If the visual is funny, then this neuron will fire. This will fire if the speech is funny, and this will fire if the text is funny. And based upon these outputs that is given by these 3 neurons, it will be fed to the second layer neuron. And in second layer, we have only 1 neuron, and this neuron will fire only if 2 of the inputs are fired. 2 of the 3 inputs are fired. What are the 3 inputs? If the visual is funny, if the speech style is funny, or if the text is funny. If visual is funny and if text is funny, we will laugh. Surely we will laugh. If the visual is funny and the speech is funny, then we will laugh. Okay. If all of the 3 fires, then also we will laugh. And based upon certain functionalities or certain activations, each neuron will fire. This is the biological neuron. And here we need to replicate this biological neuron with the artificial neuron. And this is the simple artificial neuron diagram. And we need to focus on these parts, these yellow color parts. Okay. In this neuron, artificial neuron, we have some inputs, that is X1, X2, X3, X4, X5. So we have 5 inputs. In addition to these 5 inputs, we have one more input that is always 1. Keep note that in addition to these 5 input nodes, we have one more node that is always, the input to that node is always 1. And associated with each input, we have some weights. For x1, the associated weight is W1. For the x2, the associated weight is W2. Similar for x5, the associated weight is W5. And for this one, the weight associated is W0. Normally, W0 can be referred to as bias. If we studied about the soft computing, we know about a term known as bias. And here, this is the bias term. Okay. Then we have the Z1. Z1 means it's the activation form. It's not the activation, it's the summation unit. It will perform the summation of this. For example, this x1 is multiplied with w1, that is x1 into w1 plus x2 into w2 plus x3 into w3 plus x4 into w4 plus x5 into w5. In addition to that, we need to sum this component also. What is this component? 1 into b. And that summation result is z1. Okay, that summation result is z1. Z1 can be any value. And this value needs to be fed to an activation function, and this activation function will receive the inputs or receive the outputs from this z1, and it will convert to another set of values. And this value is given as the y dash, and this is the output of this artificial neuron. And this is the basic diagram of this artificial neuron. I will explain a little bit more. Instead of x1, x2, x3, x4, x5, I'm going to replace with some scenario. If you need to purchase a laptop, we need to consider several factors. Basically, the price of the laptop heavily depends upon the processor speed, RAM size, and hard disk size, then compared to the screen size and battery time. Okay, so here x1 is the screen size, x2 is the hard disk size, x3 is the processor speed, x4 is the RAM size, and x5 is the battery time. But whenever we need to predict the price of a laptop, the feature that is more important is the processor speed, RAM size, and the hard disk. So the associated weights of this input. What's the hard disk weight associated with the input of the weight associated with this hard disk size? That is the W2. Here W2 have more importance weightage. Here the W3 have more importance, and W5 also has more importance when compared to W5 and the W1. And in similar fashion, we are computing the summation as earlier itself. We are computing this Z1 and we are giving that into a activation function, and it is represented by G of Z1. Z1 is this summation unit. Okay, and it will give an output, and that is the cost of the computer. And this can be treated as a regression problem. Okay, we are estimating the cost of a computer. That means it gives a new predicted value. If you're giving a new predicted value, then we can say that it's a regression problem. And this is only the concept of a single artificial neuron. Again, what all are these features? In the earlier slide, I already told that for predicting the price, these all are the features. Screen size, hard disk size, processor speed, these are the features. Okay, and in this case, we are going to consider different type of problems, and we will check what all are the features regarding that problem. For the housing price, what all are the features? The number of rooms is one of the feature, house area, air pollution, distance from facilities, economics, indexity, security ranking. These all are the features that are required to compute the price of the house. For detecting whether the mail is spam or not spam, in order to do that, we need to have some features. What are the features? The presence or absence of certain email headers, the email structure, the language, the frequency of specific time. These are the features for the spam detection problem. For speech recognition problem, noise ratio, length of the sound, relative power of sound. These are the features of speech recognition. Similar to that, for each category, we have different set of features. But in earlier case, I told you that for extracting the features, we need to have some feature extraction techniques. And based upon, if you know the problem exactly, you can go with the feature extraction process. But if you're not thorough with the feature extraction process, I won't suggest that. Okay. So for the image classification category, we are focusing at this point. Okay. For the image classification, what all are the features? Pixel values, curves, edges. These all are the main features. Then we need to understand the different type of neural networks before going into the depth of deep neural network. When we look at this neural network, you can see that it contains two layers, and basically, okay, this is one layer and this is another layer, and this is represent each node in this second layer is represented by circle, but here it is represented by a square. We don't actually count this input layer. Okay, we don't actually count this input layer. Input layer, each node is represented here as square. But here we have the second layer, and it can be treated as the output layer because this layer is actually interacting with the outside world. Okay, and in this output layer, each node is represented by a circle. And in earlier case, I described about a single neuron. You can treat that neuron as a single circle. Okay, likewise here we have three artificial neuron. Here we have three artificial neuron. In addition to that, we have four input features, that is x1, x2, x3, x4, and these all edges have associated weights with these inputs. And here we have only one layer. That's why we call this type of neural network as single layer neural network. Keep that in mind, because we normally say that it's a dual layer neural network. It's not a dual layer neural network. This is the input layer. Okay, this is the input layer and this is the output layer, but we consider only this one. Okay, here we have only one layer. That's why we call the name as single layer neural network. But in this case, we have the input layer, we have the output layer. In addition to that, we have an hidden layer. We have an hidden layer. So how many layers will be there? We have input layer. We are not going to count that input layer. These are the inputs that are directly given to the network. But this node in this hidden layer can be treated as a single artificial neurons. So we have totally 1, 2, 3, 4, 5, 6, 7. Totally 7 neurons are present in this neural network. And we have two layers. That's why it gets its name multi-layer neural network, or we can call it as a shallow layer, shallow neural network. And next is the deep neural network. And this layer is referred to as the one thing. This layer is referred to as the hidden layer. Okay. And in this case, we have two hidden layers, and this is the input layer and this is the output layer. When we have two or more hidden layers, we can call that neural network architecture as deep neural network. Okay, when we have two or more hidden layers, then we can call that neural architecture as deep neural network. Again, let's go into the depth of this neural network. We have this blue, all the nodes that comes under this blue shade is the input nodes. And it is specified that here there is no computation is performed in any of the input nodes because these are the direct features. They just pass on the information to the hidden nodes. And this is the hidden nodes. These are the hidden nodes, and these are also hidden nodes. And hidden nodes have no direct connection with the outside world. We can see that from this picture itself. Okay, only this layer have the connection with the outside world. And in this case, each neuron will perform some computation inside that, and the output will be fed to the next layer. And here also some computation will be performed, and the activation result of this activation function will be fed to the output layer. And in output layer are responsible for the computation and transferring the real outputs to the outside world. Okay, this is the example of deep neural network because here we have two hidden layers. When we have two or more hidden layers, we can call it as deep neural network. That's why I gave this figure, this. Again, we need to have some understanding. This is another one recipe. What do you mean by linear versus non-linear problem? Here we have two classes. These green dots belongs to one class and blue dots belongs to another class. But these two clusters can be separated by a straight line. When we look at this figure, we can understand that these two classes can be separated by a straight line. If you're able to separate classes with a straight line, then we can call that type of problems as linear problem. Linear problem. Suppose you have this graph, and when we look at these green and blue dots, we can surely tell that we cannot separate this with a single line. We need to have some another mechanism. Here, these two set of data points can be classified using a circle. So circle is a non-linear thing. So we can say that it's a non-linear type of problem. And majority of the problems in all problems in computer vision and in natural language processing belongs to this category. And basically, when we use regression problems, we can solve it using this linear problem. And I'm going to focus on this non-linear type of problems. I hope that you got some intuition on this. Again, this is a question for you. This is the representation of AND gate. You know that when the input is 0, 0, the output will be 0 for AND. For 0, 1 and 1, 0, the output will be 0 for AND. And for 1, 1, the output will be 1. Here, these are the outputs and these are the output. That means for 0, 0, we have the answer 0. 0 is represented by black. For 0, 1, we can represent the answer will be 0. Again, it's a black. Here also, it's a black. For 1, 1, the answer will be 1. That's a white dot. Likewise, for OR, in our case, we will get the 0 output for the input 0 and 0. And for all other case, we have the output as 1. And for XOR, for 0, 0, we will get the output as 0. For 1, 1, we will get the output as 0. And for other combination, we will get the output as 1. So out of this, which all are linear problems and which all are non-linear problems? That's a question for you. You can give that in the chat box. Which all are linear problems and which are not linear problems? It's a simple logic. Whether you got the concept that I told? Okay, okay. And or are linear type of problems because we can separate this with a single line. Okay, we can separate. Look at the cursor point position. We can separate this with a single line. And in the case of OR, we can separate this with a single line. But in the case of XOR, we can't solve this with a single line. We need to have some non-linearity that needs to be introduced in XOR problem. So this is the answer. This is the answer for that. Again, one thing that we need to note is that for OR gate, for implementing OR gate, we can use single layer neural network. With a single layer neural network, you can replicate the OR gate. And for the AND gate also, you can use the single layer neural network. But for the XOR gate, we can't use the single layer neural network because it's not a linear type of problem. So we need to have multiple layers. For non-linear problems, we need to have the multiple layers. That's the basic concept. When we look at this figure, we have one hidden layer, we have an input layer, and we have an output layer. Here, one is the input, and to the first node of the first hidden layer, to the first node of first hidden layer, what will be the input? 1 into 3. This is the weight. Okay, this is the weight. 1 into 3 plus 2 into, this is the weight. 2 into 1. 1 into 3 plus 2 into 1 plus bias time 1. Okay, that will be the input to this neuron. That will be the input to this neuron. And that value is referred to as Z1. That value is referred to as Z1. And we need to pass that Z1 to an activation function. That will convert that values into another range. But if you're not using any activation, keep this in mind. If you are not using any activations in a single node, then this neural network is similar to this neural network. This neural network is similar to this neural network. This is a single layer neural network, right? This is a multi-layer neural network. This is a multi-layer neural network, and this is a single layer neural network. But both the inputs are same, 1 and 2. Here also 1 and 2. If you compute the output for this, the output for this neural network is same as the output for this neural network. What's the reason? Because here we are not using any activation function. So the main note is that hidden layers become ineffective. Hidden layers become ineffective when the hidden nodes have linear activation function. Linear means we are not going to introduce any non-linearity in the network. So again, this is the figure of a neural network. We have a concept known as parameters. Okay, we have a concept known as parameters in deep neural network, and there is another terminology known as hyperparameters. The parameters are the things that the system needs to be learned, and we can say that that parameters are the brilliance of the entire neural network. That parameters are the brilliance of the entire neural network. So what all are the parameters? The weights are referred to as the parameters. Weights and biases are referred to as the parameters. Okay, weights and biases are referred to as the parameters. So how many weights are there in between first input layer and the hidden layer? You can give that in the chat box. How many weights are there between the first input layer and the first hidden layer? How many weights are there in between the first input layer and the first hidden layer? I'm asking you about the first two layers, right? Input layer and the hidden layer. Yeah, we have around, because we have three input nodes, and here we have 4 nodes in the first hidden layer. So 3 into 4, that means we have 12 connections. 12 connections means we have 12 weights. But one more thing that we need to notice that for each neuron, there is a bias associated with that. For each neuron, there is a bias associated with that. But for the input nodes, we don't have any bias. Okay. For the input nodes, we don't have any bias. But from here onwards, for each node, we have one bias each. So bias are also learnable parameters. So weights and bias are the learnable parameters. In between the input layer and the first hidden layer, we have 12 weights. In between the hidden layer 1 and hidden layer 2, we have 16 weights, because 4 into 4 16. Plus in between hidden layer 2 and output layer, we have 4 into 1, that is 4 weights. Totally 12 plus 16 plus 4 weights are there. In addition to that, we have some biases. How many biases are there? Here we have 4 nodes, so we have 4 biases plus 4 biases plus 1 bias for the output layer. So we have totally around 9 biases. So the total number of learnable parameters are, okay, here we have 9 neurons. So 3 into 4 plus 4 into 4 plus 4 into 1, that is 32 weights, and 4 plus 4 plus 1, that is 9 bias. Totally we have 41 learnable parameters. These are the parameters that needs to be learned by our system. Okay, these are the parameters that needs to be learned by our system, and these weights are referred to as the brilliance of the entire deep neural network. So in order to understand the deep learning basics, this is the workflow. Firstly, we need to get the data. That's the data set. We need to clean and prepare. Clean and prepare means we need to, if you need to pre-process, you can pre-process at this stage, and all comes under this cleaning, preparing, and manipulating data. Then we are directly going to train the model with the artificial neural network. Here there is no feature extraction process. Directly the feature extraction process will be carried out by the deep neural network itself. And if the model is perfect, we are going to test the data. And if the testing data is good, okay, we can release, or we can take that model and directly deploy that in the real world applications. But if the model is not perfect, then we need to again improve. This is the maintenance part. This is the workflow of the deep learning project. Here I am showing you some examples of the famous dataset. First dataset is the MNIST. MNIST, this is the MNIST dataset. We have around 60,000, we have around 70,000 images. Okay, we have around 70,000 images. Out of that, 60,000 images can be used for the training purpose. Listen, out of that 70,000, 60,000 can be used for the training purpose, and the rest of the 10,000 can be used for the testing purpose. And here, for each image, we have the associated label. So this is a labeled data set. Okay, MNIST is a labeled data set. And for each image, we have 28 cross 28 pixels. That means we have 28 cross 28 means it's 784 pixels are there for a single image, and it's a grayscale image. And if it's a grayscale image, we know that then each image have only one channel. Next, we have the CIFAR 10. CIFAR 10 means we have 10 classes. Okay, CIFAR 10 means in MNIST we have only 10 classes because digits are from 0 to 9. In CIFAR 10, we have 10 classes, and all these images are color images. For example, this is the image of a frog, this is the image of a truck, and this is the image of a truck, this is the image of a deer, and we have 10 classes, and each image is 32 cross 32 pixels. 32 cross 32, not pixels, 32 cross 32 color image. And in this case, it's a color image, so the channels number of channels will be 3. So the total number of pixels will be 32 into 32 into 3. Okay, 32 into 32 into 3. That much of pixels will be there for each image, and associated with each image, we have a label like numbers 6, 9, 9, 7. Here 6 means it's a frog, 9 means it's a truck, 2 means it's a bird. Likewise, for each number, we have a corresponding class. CIFAR 100 means, this is the CIFAR 10 example. CIFAR 100 means we have around 60,000 images belonging to 100 categories. Here we have 60,000 images belonging to, here we have 60,000 images belonging to 10 category. In the case of CIFAR 100, we have around 100 categories. Okay, this is the example of the data set. Again, how we are going to split the data set? This is a not a hyper parameter. This is a choice that needs to be handled by us. If we have only 10,000 samples, then 80% of the original data can be used for the training purpose, and rest 20%. That means we can use 1,000 for the validation, and we can use 1,000 for the testing purpose. If you have 1 lakh images, if you have 1 lakh data points in your data set, then 99,000, not one, this is not 1 lakh, this is 10 lakh. If you have 10 lakh images, then 9,90,000 images can be used for the training purpose, and remaining 5,000 can be used for the validation, and 5,000 can be used for the testing purpose. Here the split should be done based upon the data set that you have. If your data set have a huge size, then you can vary the percentage for the training, validation, and split. If you have a few images in the data set, then the right split will be 80-20%. 80-20% means 80 for the training, and 10% for the validation, and 10% for the testing. But one thing that we need to note is that here the training data and the validation or test data must be disjoint. There should not be any common data in between this. Okay, and there are some terminologies like shuffle and split. Shuffle and split is one of the technique to randomly distribute all the images in the data set. And there is also one technique known as stratified sampling. If you're interested in that, you can further check on these topics in the deep learning specialization. Okay. Then again, I'm going to unbox this black area. This is the black box. Okay, I'm going to open this. In the case of deep neural network, we are directly giving this image to the neural network. So how many features that you are going to feed into this neural network? This is an image of, this is the image of a cat, and its resolution is 256 into 256. Since it's a color image, it has 3 channels. So the total number of pixels will be 256 into 256 into 3. Okay, 256 into 256 into 3. That much of pixels you have. And these pixels can be treated directly as features. Okay, that's the main important point in deep learning. These features can be directly treated as features in deep learning. But in machine learning, we need to extract the features using some feature engineering process like shift, hog, surf. But in this case, we don't need any such mechanism. We can directly give that pixels to this neural network. Here, there is a number known as 196608. Here, 256 into 256 into 3, and the output of that value is this one. Okay, 196608. You can give that much of pixels to a neural network, and neural network will automatically learn all these stuff. For a perfect neural network, perfect or ideal neural network, if you give the image of a cat, here we have three classes. One is the, that means if you have three classes, then we have three nodes in the output layer. If we have three classes, then we have three nodes in the output layer. In the case of feminist, we have 10 classes. At that case, in the output layer, how many nodes will be there? 10 nodes will be there. For each node, it represents one value. Okay, for first node, it represents the 0 digits. Second node, it represents the 1 digit. Likewise, here we have three classes. For that, we use three nodes. And in the case of a perfect neural network, if you give this image to this neural network, then it should output 1. It should output 1. And for the dog, it should output 0. And for the others, it should output 0. So if you give the image of a cat, the output should be 1, 0, 0. If you give the image of a dog, then the value will be 0, 1, 0. And for other type of images, rather than using this cat or dog, then the output will be 0, 0, 1. But this perfect neural network is very difficult to obtain. Okay, normally what happens is that there will be some variations in the result. For example, if you give this image, we will not get any perfect neural network. But if you are giving this image, you are getting a value of 0.97. Okay, you are getting a value of 0.97. And for dog, it says that it's 0.01, and for others, it says that 0.02. So totally, when we sum up, we will get the value of 1. This is the probability. Okay, this is the probability term. So what will be the error? So what will be the error? Actually, it should output 1. But the real output that is obtained from the neural network is 0.97. So the actual output, real output is 1 minus 0.97. That is the error here. Here, what should be the error? We expect it as 0, but the neural network gives the value as 0.01. So the error, what will be the error? 0 minus 0.01. What's the error here? 0 minus 0.02. So we need to sum up all these errors, and based upon these errors, we need to again train this neural network. After a long time, it will automatically, the weights in the neural network will be automatically adjusted based upon these errors, and finally we will get a perfect answer for this. Okay, this is the concept behind this deep neural network. Again, weight denotes weights and biases. Weight denotes how much the feature matters in the model. I already explained this in the prediction of the price of the computer. Higher the weight means, for that particular feature, we need to give higher importance. And generally, weights are initialized randomly. That's one of the important point. Normally, when we start the deep neural network, we don't initialize with zeros. We don't initialize with zeros. We need to initialize it randomly. And we have the libraries for that. It will automatically do the random initialization during the starting time. And this is the summation unit. Output will be the activation function in bracket. We know that weights comma inputs. That means x1 into w1 plus x2 into w2 plus x3 into w3 plus likewise, plus there is a bias term, and dot product up to this point will be the z, and this z will be given to the activation function. Sorry, this z will be given to this activation function, and the output will be the output that we obtain from the activation function. This is the concept behind the weights and biases. When we increase the weights, the steepness of the curve will increase. Here you can note that I am using sigmoid as the activation function. This 0.05 is the weight and x is the input. 0.5 into 0x. In another case, I am using sigmoid of 1 into x. Here the weight is 1. In another case, I am using the weight value as 2 into x. For 0.5 into x, the color is red. Here we can note this red color. Here the steepness is less. But when we increase the weight value, when the weight value is 2, the steepness is too high. So when we increase the weights, what will happen? The steepness of the curve will increase. And when we decrease the value of the weights, then the steepness will be reduced. This is the concept regarding the weights. And in the case of bias, here again I am going to use the activation function as sigmoid, and in this sigmoid function I am using 1 into x. 1 is the weight and x is the input. In all these three cases, I am freezing the weight as 1. Okay, in all these three cases, I am freezing the weight as 1. But here I am changing the bias value. For the red color, I am giving the bias value as -5. For the green color, I am giving the bias as 0 value. And for the blue color, I am giving the bias value as 5. So when we increase the bias, we can find out that this curve will move toward left. Okay, when we increase the bias, this blue curve will move towards the left. When we decrease the bias, the curve will move towards the right. But here steepness does not change as far as the weights are freezed. Okay, as far as the weights are freezed, the steepness will not change, but the curve will move right to left depends upon the bias term. Again, I need to explain why we use GPUs. Okay, for that, I need to show this demonstration. Here, these are some of the weights. We have two hidden layers and one output layer, and we have this input layer. And these are the weights, 1, -2, and this is the bias associated with this. Not the bias, this is the bias where always it's 1. And again, I'm initializing all these things. Okay, here I'm not going to use any bias. That's why it gives the value 0. And this is the input value, 1 and -1. So here, what will be the input that is given to this node? We can calculate 1 into 1. Okay, 1 into 1 plus -1 into -2 plus 1, that is 4. Okay, that is 4. This is the Z value. Okay, this is the Z value. I need to give that Z value to an activation function. So I'm going to use a sigmoid function. Sigmoid equation for the sigmoid function is like this: 1 by 1 plus 0 is to minus Z. So here, this 4 can be given to this Z value, and we can now obtain a new value. This is 0.98. Here we are introducing some non-linearity by using this sigmoid function, and we will get the output of this node as 0.98. Similar to that, we are computing for the second node, and this 0.98 is fed to the next layer. So 0.98 into 2 plus 0.12 into this -1 plus 0 bias. That will be, and that value is fed to the sigmoid function. Again, that value will be 0.86, and for this node, the value will be 0.1. Similar to that, finally, we will get the output as 0.62 and 0.83. Okay, similar to that, we will get the output as 0.62 and 0.83. Again, if you give another values for this neural network for 0, 0, again we are moving like this, and at the output layer we are getting like this 0.51 and 0.85. So in the earlier case, we are giving the input as 1 and -1, and for that we will get this as the output. And when we give the values as 0 and 0 for this neural network, we will get the values as 0.51 and 0.85, 0.51 and 0.85. So I already told that we use GPUs for deep learning purpose. GPUs are good with matrix operations, okay, or matrix multiplications. So how it computes the output through matrix operation? Let's look. You need to have a clear understanding on this. In the first hidden layer, we have one node. Okay, in the first hidden layer, we have first hidden node. And to this hidden node, what are the weights associated with this? Here there is a 1, and to this node there is another weight known as -2. Okay, so 1 and -2 needs to be placed in a single row. Okay, 1 and -2 needs to be, look at this, 1 and -2 is the weights associated with the first node of the first hidden layer. Likewise, for the second node in the first hidden layer, what all are the weights associated with? This is -1 and 1, -1 and 1. -1 and 1 is written in the second row. And this is the weight matrix. Okay, this is the weight matrix. And we are going to again multiply that with the inputs. We already know that we need to multiply x1 into w1 plus x2 into x2 into w2 and plus x3 into w3. Similar to that, these all are the weights, and input can be treated like this. Okay, so this weights into the input. We need to perform some matrix multiplication here, and again we need to add the bias. What are the bias? Here 1 and 0. So we can represent it as 1 and 0. 1 is associated with this neuron, so we return in this first row, and 0 is associated with the second neuron. That's why we wrote that in the second row. Okay, then we are performing that and we are getting the value as 4 minus 2. This is similar to that we computed earlier. Okay, then this value needs to be given to the sigmoid activation function. We can apply the answer to the sigmoid activation function, and the sigmoid activation will give the values as 0.98 and 0.12, which is similar to the output that we obtained in the earlier case. This is the concept that the GPU is performing for the deep neural networks. Okay, this is the metrics. That's why I am saying that all the things are happening through this matrix multiplication, and GPUs are good at that. And when compared to this CPU, because GPUs are specialized for that type of operations. And in the gaming purpose also, majority of the operations are matrix operations. Okay. Again, what's the purpose of activation functions? So the main purpose of the activation function is to introduce some non-linearity to the network. So if you need to introduce some non-linearity, and if your problems are non-linear problems, then you must use activation functions. If you're not going to use any activation functions, then it is similar to that of linear regression model. Linear regression model means if you need to predict the price of a house or you need to predict the stock price, you don't need to use any sigmoid function. Okay, because they are not non-linear problems, they are linear problems, and you can directly go with the linear type of activation functions. But for the images, audio, speech, for that type of problems, you need to go with the non-linear activation function. So let's look some of the activation function. One is the sigmoid activation function. This is the equation for the sigmoid activation function. And we need to firstly compute the summation unit, that is the Z, and we need to give that Z. Here it is represented as X. So you need to place that value here. And here the sigmoid activation function will take this Z value and it will convert that value in the ranges between 0 and 1. Okay, keep note that. Here it will take any values and it will output the value in between 0 and 1. This is the graph belonging to that. This is the structure of the sigmoid function. We know that this is the 0 position and this is the 1 position. And if you're giving a large negative value to this function, then the output will be always 0. And if you're giving a large positive value for this x, then you will get at this position, that is always 1. And all the values in between, you will be at this curve position. Okay. This is the concept of sigmoid function. And again, this is the hyperbolic tangent. This is another type of activation function that we can use. In this case, it is similar to that of sigmoid function, but what happened is that instead of converting all the values between 0 and 1, it will convert the values in between -1 and 1. Earlier, sigmoid function is not zero-centered, but here this hyperbolic tangent is zero-centered. Zero-centered means here the middle value belongs to this 0 value. Okay, and this is the -1 and this is the +1 area. This is one type of activation function. And next is the ReLU activation. This is the most popular type of activation that we used in the deep neural networks. This is a simple type of activation function. You need to give the value to this equation, max of 0, x. For all positive values, it retains the positive value. Okay, for all positive values that it retains that positive value. But if you're getting a negative value, then 0 will be the output. This shows like that. Okay, for any negative values, it gives the values as 0, and for all positive values, it will maintain as it is. Okay, this is the ReLU activation function, and this is the most commonly type of activation function that is used in every deep neural network. Similar to that of, we have another type of activation function, that is a leaky ReLU. Instead of giving for all negative values, in earlier case we have the value zeros. Instead of avoiding that zeros, we are multiplying that with a value known as a. This a can be any value 0.01 or 0.001, so that we will get a slight slope here. Instead of getting zeros, for all negative values, we will get the zeros. Instead of in the case of ReLU, but in the leaky ReLU, for all the negative values, we will get a slight slope. So there is some specific purpose for this slight slope. I will explain that in the later slides. And this is the popular type of activation function, softmax, which is basically used in the output layer. In earlier case, for the image classification type of task, we know that for the digit classification we have the 10 nodes in the output layer, and each node belongs to one digit, and it gives the probability. And for getting the probability, we need to use softmax activation function at the output layer. We need to use softmax function at the output layer, and we can use redo at all the hidden in the all hidden layers. And but at the output layer, we need to use softmax. Okay. Again, we need to compute the loss. What do you mean by loss? In earlier slides, I already explained that we get a value of 0.97 for a cat, but for a true network, it should give us 1. So what will be the loss? 1 minus 0.97. 1 minus 0.97. Here, y is the output that we obtain from the neural network, and di is the correct output that we expect. In the case of in the earlier case, this is 1 and this is 0.97. So what will be the error? 1 minus 0.97. That is 0.03. So why do we need to square all these stuffs and then dividing it by 2? The purpose is that, uh, understand that for the first node, you will get an error of zero point 0.7. Imagine that for the first output node, you will get the error of 0.5. In the second node, you get the error of negative zero point 0.5. Okay. In the third node, you get the output as you get the error as 0. So what will be the total error? In the first node, you get errors as negative 5. In the second node, you get errors as positive 5, and in the third node, you get the errors as 0. So when we sum up negative 5 plus positive 5 plus 0, that is again 0. It says that there is no error in the network, but actually there is error. Okay, actually there is error, but when we sum up all these stuffs, we will get the value as 0. 0 means there is no error. We need to avoid that situation. In order to avoid that situation, we are actually squaring the term. If you are going to square that error, then we can avoid that condition. And basically, backpropagation uses gradient descent algorithms. And in that, when we need to apply the partial derivatives, normally we need to differentiate all these stuffs. And when we differentiate this value with respect to yi, we know that the value will be 2 into di minus yi into minus 1, and this 1 by 2 is already there. There is a two term in the numerator, and that 2 term and the denominator 2 term will be cancelled out each other. And for the cancellation purpose, we are giving this 1 by 2. I don't know how many of them understand this concept, because it's a long journey. Around 194 slides are there. It's very difficult to cover up all these stuff, but I will give you some intuition on this. These all are my workshop slides. Again, there are some types of loss function. One type of loss function is the mean squared error, and it is basically used for the regression type of problem. And this is another type of loss function, cross entropy loss, and it is basically used for the classification type of problems. That means it is basically used for the image classification or image detection type of problems. And not going to explain all these things. And if a problem type is binary classification means you have only 2 classes, cat and dog. There is no other animals. Okay, you have two classes, and the problem is a binary classification. In that case, you can use the sigmoid activation function, the loss layer, and the loss function that you need to use is the binary cross entropy. In the case of multi-class single layer classification, multi-class means we have multiple classes. In MNIST, we have 10 digits. Okay, 10 digits means more than 2 classes. So it's a multi-class problem. And for each image, if you're giving the image of a 0, then the label should be 0. Okay, that's a single label. For each image, there is only a 1 label associated with that. In that case, we need to use softmax as the last layer activation, and the loss function you need to use is the categorical cross entropy. In the case of multi-class, multi-label classification, for example, suppose I am going to train a neural network that contains only 2 classes, cat and dog, And the training goes perfect. And if I'm giving the image of a cat, it needs to say that the image belongs to cat. If you give the image of the dog, it needs to say that it's a dog. Suppose, or imagine that you are giving an image, and in that image, we have the pictures of both dog and cat. Then what will be the output? Again, it's a confusion. Okay, if you are giving an image, in that image itself, we have that two animals, cat and dog. Then what will be the output? It needs to say that this image contains both cat and dog. In that type of classification, we can refer that type of classification as multi-label classification. For a single image itself, we have different type of classes. For example, if you need to classify a movie, the movie can belongs to different category. It can be belongs to emotional based or funny. It can be emotional and funny. Okay, it can be emotional and funny. Likewise, for one film itself, we have different labels. And for that type of activation type of problems, we use sigmoid as the last layer activation, and loss function that we use is the binary cross entropy. And for regression type of values, we don't need any last layer activation, and loss function should be mean square error. Okay, mean square error. And I already told that if you're not going to use any activation function, then we can solve regression problem. This is similar to that. If the regression values are between 0 and 1, then we need to use the last layer activation as sigmoid, and the loss function that you need to use is the mean squared error binary cross entropy. Again, I'm not going into the depth of backpropagation, but I will explain that with this diagram. I am actually flipping that neural network into this manner. You can view this as a first hidden layer. Okay, we can view this as a first hidden layer. You can view this as the second hidden layer. This is the first hidden layer, and this is the second hidden layer. This is the output layer, and this is the input. If you are giving the values of x, then the actual value will be y. For xy pair, if you are giving the value of x, then the actual value should be, actual target should be y. But the neural network gives the output as y dash. So what's the loss? Y minus y dash. This is the loss. So after computing this loss function, how can we compute the loss function? By using the earlier technique like binary cross entropy or mean squared error. Using that type of loss function, you can compute the loss. And once you find out the loss, you need to change the weights of the neural network. Inside, in between each layers, we have some weights and biases. And based upon these laws, we need to adjust these weights and biases. And in the later time, what happens is that if the training is perfect, then the loss function, then the loss will approximate comes to 0 value. Okay, then the loss function will comes to a very low value. At the time, we can stop the training. And once we stop the training, we can take out the model. And if you're giving an image, it will predict what the image exactly is. And here you need to note is that here the weights and biases are the brilliance learned by this network. And this whole concept, and based upon this law score, there is a terminology known as optimizer. We have different terminology. We have different type of optimizers like Adam optimizer, RMS probe. We have several type of optimizers, and based upon these optimizers, we are going to update the weights. Okay, weights are updated based upon these optimizers. Again, this this can be viewed as a loss function. Okay, this can be viewed as a loss function. Suppose this y-axis shows the error, this y-axis shows the error, x-axis shows the weight. This is the loss function. Okay, at the initial stage, you are at this position. Imagine that at the initial stage, you are at this position. So at this position, the weights are low. Okay, at this position, the weights are low, but the errors are very high. You need to actually come to this position. Here, the loss is very low. Here, the loss is very low. You need to come from this point to this point. So what you're going to do is that, what's the slope of this point? Actually, it's a negative slope. So you need to move in the opposite direction of that slope. Here the slope is negative. So you need to move in the opposite direction of that slope. If you are moving in the another name for the slope is the gradient. Gradient and slope are both same terminologies. So you need to move in the opposite direction of the gradient. That's why it gets the name gradient descent. You need to move in the opposite direction of the gradient. Descent means you need to move in the opposite direction of the gradient. So if the slope is negative and negative of negative slope means it's a positive. So we are going to increase, we are going to come to this position. But when we are going to come at this position, what happened? From this position, the weights are actually increasing and you reach at this position. This is the global minimum. Global minimum means in this curve, this is the position where we getting the lower loss. And this is the right spot where you need to be found. And actually, this is found out by the system. And suppose you are at this point itself. Suppose you are at this point, and here the slope is positive. So you need to move in the opposite direction of this slope. So negative of positive value. That means we have some weight, and you need to move in the opposite direction. If you are moving in the opposite direction, you come at this point. Here, the initial weight is higher, but when we reach at this point, the weight will be actually decreased. Okay. So this is the basic concept of the gradient descent. Again, in this is the weight updated rule. This is the weight updated rule. Weight updated rule means we have the old weight minus alpha is the learning rate, dou j by dou w. Dou j by dou w is computed by the partial derivatives. I don't have the time to explain all these things. But one thing that you need to note is that we are computing the slope, and that slope is multiplied with an alpha, that is the learning rate, and we are subtracting that value from the old weight. Then we will get the new weight. Likewise, for the bias also, the system is automatically updating based upon the loss. This updation will be carried out by the use of optimizers. Okay, then I'm skipping some of the slides. I need to give you a live session on some projects. That's why I'm skipping slides. If you're going to use the sigmoid as the activation function, there is a problem known as vanishing gradient problem. Okay, this is the problem. For when we use sigmoid as the activation function, what will happen? For higher positive values, the output will be continuously 1. If the output value is continuously 1, that's actually a horizontal line. For horizontal line, the slope is actually 0. For the horizontal line, the slope is actually 0. If the slope is 0, then we don't have any weight update rule. What's the weight update rule? New weight equal to old weight minus alpha into dou j by dou w. Here the alpha into dou j by dou w becomes 0. In the case of, say, if you are going to use this sigmoid function. And if you are going to use that, what happens is that instead of learning this phase, it will learn this structure. Okay. Instead of learning this phase, it will learn this structure. Because the earlier layers of the neural network will learn about the edges, but the later layers will learn about the complex type, complex objects like nose, ears, and that will be learned. But when we move back to the earlier layers, the gradient will become 0, so that there is no learning. So there is no learning will happen at that point. And if there is no learning happen at that point, then the symbol edges will not be learned. If the symbol edges will not be learned, then the output will be look like this. Okay, now I'm stopping one thing. Okay, I'm skipping. Again, there is a network known as convolution neural network that is basically used in deep neural networks, and we have several type of applications like classification. Classification means given an image, you need to detect what the image is, or you need to classify what the image exactly is. Detection, then there is another terminology known as classification plus localization. Given an image, you need to actually find out where the cat resides. Okay, where the cat resides. You need to get the bounding box of that cat. Okay, if you are using this localization property, then we can call that problem as classification plus localization. Instead of telling that this image contains cat, it will also specify the location of the cat. And both belongs to a single object category. And in this case, this is the object detection. Object detection means if you have multiple objects, then all objects will be detected and it will be labeled according to that. And that problem is referred to as the object detection. Instance segmentation means we can segment out each object based upon the certain features, and we can reuse this segmented parts. And this terminology, this type of problem is referred to as the instance segmentation. Then neural art transfer. Neural art transfer is another problem. For example, you have the image of a Mona Lisa, and you have the artistic style of a different artist, and you can combine both the style and the original image to get a new image like this. This is the artistic representation of the Mona Lisa. Okay, and this is referred to as the neural style transfer. This is the original image, and this is the content image. This is the style image. We are merging this content image and style image to get the new style, that is the neural style transfer. Next is the image captioning problem. Image captioning problem means if you are giving the image to the network, it will say what the image is. Here, an young boy is playing basketball, and when we give this image, it will say that two dogs play in the grass. And for this type of problems, we need to use recurrent neural networks, RNN, along with the CNN also. So these are some of the cases. Okay, I'm skipping this slide. So I have only one thing. It's the right time to study about AI, and this is a huge field. This is actually a huge field, and you need to have some interest on specific areas like computer vision or natural language processing. It's very difficult to study whole machine learning because machine learning contains so many subfields, and it's very difficult to understand all the concept of this. So you need to be specific. I'm actually specializing in computer vision, and for computer vision problem, I'm going to solve a computer vision problem using these machine learning and deep learning frameworks. And thank you for your attention. But before stopping my session, I just want to give a live demonstration of neural style transfer. So now I'm going to, can you wait for 5 minutes?
Yes, yes, please.
Okay.
Go ahead. Go ahead.
If you have any queries, you can directly give that in the chat box. Can you see my whole screen?
Yes.
Okay, it is actually loading. Basically, I'm using all these libraries like TensorFlow, then OpenCV. We need to have GPUs for all these computations. That's one of the biggest challenges. With the Colab, we can program up to some level, but if you have GPUs, you can do a lot of stuff. So this is the program for neural R transfer. It will take some time for updating the parts. So here I am going to give an image and also a style image. Both styles will be merged into a single image. Let's look at this. This is a type of pre-trained models. I am actually using the pre-trained models obtained from the Google itself. Can you see this? Can you see this?
Yes, Nithin, yes.
Okay, this is the original image, and to this original image, a style is applied. Okay, to this original image, a style is applied, and based upon that style, this input is transferred to this output. And let's have a look on another type. I can give another style, uh, the same image. Instead, I am applying a starry night style. Again, this is another style. This is the style of another artist. I'm using his style to transform his input image to the corresponding output. Okay, and these are some of the examples of the neural transfer. And you can directly do that using the OpenCV library. And I can show you one more example of image classification. I will stop within 5 minutes. So given an image, it will automatically predict what the image exactly is. So if you give the image of a eagle, it shows that the label is eagle with 100% accuracy. Okay, with 100% accuracy. These all are pre-trained models. I am reusing the weights and along with the architecture of the neural network. I hope that you got some understanding on these techniques. But for the proper understanding, it will take time because in order to understand all these stuff, we need to have at least 2 or 3 days complete. Okay, thank you for listening, and I hope that you will surely learn some new fields in this AI. Thank you. Hello, sir.
Lakshmi Miss, go ahead.
Hello, am I audible?
Yes, ma'am.
Yes, yes.
Now it's time for the Q&A session. If you have any queries, please post it in the chat, or you can unmute your mic and ask Nithin. Do we have any questions? Okay, I think we don't have any.
Okay.
Okay.
Anyway,
Now,
thank you for the wonderful cooperation with you all.
okay, now that was a wonderful presentation, Nithin, on an exploration to the world of AI, ML, and DL. I understand that it was pretty tough to venture into something like AI, ML, and DL in such a short span of time. But as always, you handled it really well. It is always a pleasure having you with us, Nithin. I, on behalf of the entire Department of Computer Science and Engineering, would like to say that we are extremely grateful to you for accepting our invitation and finding time out for all of us. Thank you so much.
Thank you, ma'am.
Thank you, Nithin. Thank you.
Okay.
Dear participants, kindly do fill in the attendance form for today's afternoon session. Thank you. Thank you for your attention.